Hello and welcome to 8th and the last lecture in our comprehensive course of AI, ML and data science. We are at present doing chapter number 7, this, and this chapter was named Data Wrangling with Pandas. So mainly our focus is only about learning various things related with Pandas. Of course, we will have to use some other libraries, but at that time the code which we are using, that is just for example, for better explanation of the concepts, because we are going to take detailed discussion about those libraries in any case in some later chapters. We are going library by library. We took 2 chapters on NumPy. Similarly, we are taking now 2 or 3 chapters on Panda. In NumPy, we also did this SciPy. So far we have covered these 3 libraries. Of course, for giving example, sometimes I had to use matplotlib. Otherwise, the plot will not be displayed, and concept may remain unclear. Similarly, here we will also use this scikit-learn, but you should not think that yes, in this chapter matplotlib is introduced and it is over, or scikit-learn is introduced and it is over. No, we have just like separate chapters for NumPy, separate chapter for Panda. Similarly, there will be separate chapter on matplotlib and separate chapters on scikit-learn. Okay, so this was some diagram from one of the old chapters, chapter number 4, that these are various libraries. And so far, actually, we have covered Pandas, NumPy, and SciPy. This is the last lecture on data wrangling with Pandas. Now, data wrangling covers these many things: handling missing values. So wherever there are missing values or none or empty cells, then you can put either mean or median if it is numerical variable, and mode if it is categorical variable. Data type conversion. You can easily write a particular column df in square bracket the name of that column. Suppose the column is that profit, then df in square bracket in inverted comma profit, and then dot, and then you can write as type in bracket. You can write whatever type you want. So as type int, as type float, like that. So the column will be converted into that data type. I'm giving some revision also with each. Outlier detection. So outliers are extremely high values or extremely low values. Now what you will call extremely high? Then those values which are at a distance greater than or equal to 1.5 times standard deviation from median, they are extremely high values. And similarly, what are extremely low? Then those data points which are at distance less than median minus 1.5 times standard deviation, they are called extremely low values. Then duplicate creation and deduplication. Now duplicate detection. So here we can detect if a given data frame has a particular row that is getting duplicated somewhere in the entire data frame once again, and the duplication may occur over one feature, over all the features. That means if the data frame has 10 columns, then the row is exactly identical in value for all those 10 features. But sometimes you can define duplicated rows as even if it has the same value in say 3 columns out of 10, then you may want to remove them. So that is duplication at that time is defined over a subset of columns. So we have done both, and the methods are simple. Data frame df.duplicated, when you use that, will give true or false for every row. True means that row is somewhere duplicated below, and false means that row is not being duplicated. Okay, so that is one thing. Then once you find that there are certain rows which are being duplicated, so then you can say that df.drop underscore duplicates. And we have seen that drop underscore duplicate is a very powerful method, and it can be combined with least comprehension, it can be combined with lambda function, it can be combined with many other things. Then identifying and dropping single valued columns. There we saw that single valued columns do not add anything to the predictive power. In fact, they may spoil the model and introduce bias. And we also saw that such columns are simply dropped from the data frame before proceeding further with the data science life cycle. But we also saw that sometimes the original data sets may not have single valued column, but after doing some data pre-processing like aggregation, maybe group by, maybe merge, maybe sort, sometimes you may get some columns which are single valued. So checking for the single valued column must be done periodically, again and again. Okay, now we are coming to the last thing, normalizing and standardizing data, and this is very important, so please pay attention. Now here was the entire data science life cycle. Okay, so we had said that first you have to understand the problem, you have to understand the business of your client, then you have to convert his business problem into data science problem, and develop one such hypothetical model. And in this model, these constants are unknown, so you have to find the value of that constants, and that will help you to determine the value of your response variable which you are trying to predict. with the help of this variable, that is the independent variables or features. Okay. Now for that you have to load the data, which is pd.read_csv. Then you have to understand the data. You have to do exploratory data analysis, which is just now whatever 5-6 points which I described, and then you have to do some feature engineering. So this normalization is also sometimes included as feature engineering, and some books are considered normalization as a part of exploratory data analysis. But exploratory in real sense is only viewing the data but not doing anything to modify it. But here we are modifying the data, so this should ideally be called pre-processing, data pre-processing or feature engineering. Okay. Now, why these operations are required first? Then, and what is the difference between normalizing and standardizing? Normalizing means if there is a column which is having values ranging from maybe 2000 to 20,000, so that is a big range, 2000 to 20,000. So we want to do something to that column's data so that every value comes within some fixed range, say 0 to 1. Why we want to do that? Don't worry at present, but we may like to do that. That every column, every value in that column is having value between 0 to 1. And the tricky thing is that we are changing the values of the in that column, but we don't have to change the data distribution. Okay, so that means the nature of the data should remain same, so that one person builds the model based on original data and another person builds the model on that normalized data. Then both will get same result. In fact, the person who is doing on normalized data may sometimes get better result. Okay, so we are changing the magnitudes of values in a column, but we are not changing the basic nature of data. Okay, or we are not changing data distribution. What is the meaning? That will also become clear. So if you change all values so that all of them are between 0 to 1, then that process is called normalizing. But if you change all values so that all values are distributed in such a manner that the mean value of all is 0 and the standard deviation of all is 1, or the variance of all is 1, then such process is called standardizing. So both these are often called one common name, scaling. But scaling is actually used for normalizing, and standardizing is used, or you can say that, okay, scaling, fine, same word for both, but that creates confusion that whether the data was changed from 0 to 1, or whether the data is changed in some such format where the mean is 0 and the standard deviation or the variance is 1. So better to use specific word normalizing if the data is changed in this manner, and standardizing if the data is changed in this manner. 0 mean and unit variance, unit standard deviation. Okay, these steps are very, very important because there are certain algorithms which require only normalized data or standardized data. They cannot deal with the data which is not normalized or standardized. At the same time, nowadays some modern algorithms are developed which do not care about standardized data. Okay, so do not care about standardized data does not mean that they do not use standardized data, but they take even unstandardized or unnormalized data, and while their algorithm is executing to create the model, they themselves take care of the process of normalizing or standardizing. So you don't have to do that as a pre-processing. Model building itself includes the normalizing and standardizing in modern algorithms. But in short, there are two types of algorithm at present being used in data science. Some algorithms are such that they require first pre-processing. You have to normalize the data, bring all values between 0 to 1, or standardize the data, that is adjusting all values such that their mean is 0 and variance is 1. Alternatively, there are certain other, and then feed to algorithm. Alternatively, there are certain algorithm which just takes unnormalized and unstandardized data, but before building model, they internally do the process of normalizing or standardizing themselves and then build the model. So ultimately, these processes are required, whether the model building algorithm handles them itself or whether you have to do these processes manually first and then assign the normalized or standardized data to the algorithm. That is the only difference. Okay. Now here, first technique. The first technique is here called min-max scaling, or it is called normalization. Now in this technique, suppose xi is one particular observation. Okay. So in that case, if xi is observation, then this is how that observation would be changed so that the value is scaled. Okay, so what is the scale value? Then xi minus x minimum, where x minimum is the minimum value of all similar x's. So suppose there are 10 observations, x1, x2 up to x10, then you have to find the minimum value of that and that put it here. So find the difference of given observation and the minimum value and put it in the numerator, and find the difference of maximum observation and the minimum observation from the given say 10 data points and put it in the denominator. Then their ratio gives the scaled value, and this definition itself is such that it will automatically scale. The scaled value will always come between 0 and 1. Why? So let us take one example. Suppose these are some 10 observations, random values 12, 25, 7 and so on up to x10 is 22. So how to do this scaling, or that means min max scaling or normalization? So for that you have to do first find numerator xi minus x minimum. So each observation should be subtracted from each observation you will subtract the minimum value. Now here what is the minimum value? Then minimum value is 7. So 12 minus 7 5, 25 minus 7 18, then 7 minus 7 0, because minimum is also one of the observation. When you do minimum value minus minimum value, then answer will be 0. That explains why this algorithm, that is this min max scaling, will always scale the data from 0 to 1. Okay, so 7 minus 7, so answer is 0. Fine. Then 19 minus 7, so 12 and so on. So each observation, from each observation we are just subtracting the minimum value. So I am getting the numerator, okay, x minus x minimum. And similarly I also find x max minus x minimum. Now x max here is I think this 34, right? Okay, and x minimum is this. So 34 minus 7, that will be 27. Okay, so then each of these numerator should be divided with 27. So here I am doing that whatever is in the left column, that is xi minus x minimum, I am dividing by x max minus x minimum, but x max minus x minimum is 27. So 5 by 27, 18 by 27, 0 by 27, which is 0, 12 by 27, 27 by 27. Now that is the reason why the one of the value, just like one of the value must come 0, one of the value must come 1 also, because here this is itself the maximum observation, and here I am doing maximum minus the minimum actually. But in the denominator also I am doing maximum minus minimum. So then in that case it would be maximum minus minimum divided by maximum minus minimum. So that will come out to be 1. Similarly here xi minus x minimum divided by maximum minus minimum is 27 and so on. So I will say that original observations are like this, but I can express that old 10 observations as 0.185, 0.667, 0, 0.444, 1, 0.407 and so on. Now this looks very interesting, that it looks that we have changed the data completely. Is it allowed to change the data completely in machine learning or data science? Then if you do it systematically like this, then yes, it is allowed. You will see that whether you use this original data or whether you use this data, the data distribution remains exactly same. Data distribution means what? That we are seeing in the next cell where I am plotting the graph. So let us plot the graph, and therefore that matplotlib library is required. We have detailed 3-4 chapters on matplotlib, so don't worry about at present how this code is coming and all that. So we take one numpy array which is like this, which was my original observations. Then I create x minimum using numpy library. So minimum value of this x vector, okay, x array. So that is np.minimum and minimum value of this. So what will be the value of this x minimum? Obviously that value will be 7. Okay. Similarly x maximum is equal to numpy np.max of x, where what is x? X is this whole array of all these 10 values. So what is the maximum value here? That is 34. So the result here would be 34, and the result above x minimum, its result would be 7. Now calculate the scaling. This time I am doing by basic definition of scaling. So that means x, each observation minus x minimum divided by the difference between maximum and minimum. That was the definition. This is the definition of scaling. Okay. So then find that for entire numpy array. Okay. And numpy supports array wise or element wise operations. So when you do x minus x minimum, what will happen? From each of these x minimum will be subtracted. And similarly when you do x max minus x minimum, they are both are numbers. This is x max and this is x minimum. So that ratio, that difference would be just 34 minus 7 or 27. But here in the numerator will be each observation minus x minimum. Okay. So that would be like this 5, 18, 0, 12, all xi minus x minimum and divided by 7. Let us plot this, and if you plot, I am plotting the original data distribution also and the new after doing min max scaling also. And it is surprising. You can see that original data was looking totally different, 12, 25, 7, etc. And here you can see it is that only. The range is from 10 to 35. So one is maybe 12, another is 25 and so on. While new data is looking totally different, 0.185, 0.667, 0 and 1. So for the new data range is 0 to 1. So you can see that also 0 to 1. But see the data distribution. Isn't this amazing? That the data distribution is exactly identical. So that means whether I build my model based on left side data or whether I build my model based on right side data, it does not make any difference to the final inference, because I am not disturbing. I am disturbing the absolute values of the observations, but I am keeping the relative distribution and the relative strengths as it is. So this is the real thing about min-max scaling. Okay. Now this was just one column, that this is the one particular column, and we did its min-max scaling. But in practical data set, what will happen? There will be several columns, and you will have to do min-max scaling. So at that time, you cannot afford to do this kind of formula. Okay. I mean, apply formula for first column, then apply formula for second column, apply formula for third column. No. Then what to do? you have to use this library scikit-learn. It has built-in min-max scalar process. So from scikit-learn dot pre-processing, as I said, this is now no longer just the data wrangling, but we are not just observing the data, but we are actually this is not just data exploration, but we are also changing the data. So we are doing data wrangling, or we are doing data pre-processing. So from sklearn dot pre-processing, import min-max scalar and then create this data frame. So I'm creating one data frame. Let us view that data frame. This is my data frame. Now, one important thing about scaling, normalization or standardization, both, is that it can be only applied to numeric columns. Okay. So here my problem is this one column, gender, is having the string values or boolean values, whatever you say. Also, it is a single valued column. So we know that this kind of column needs to be dropped. So let us drop it by df.drop command. And now I have this particular data frame. Now I want to apply the min-max scaling. So then once you have imported this, I should put maybe this here for better understanding, because now that is used. Okay. So from sklearn dot pre-processing, import min-max scalar. Once you have imported min-max scalar, it is available to use. Then create a scalar object. This is nothing but creating a scalar object. That scalar is equal to min-max scalar. You can write any name here. You can also write my scalar, or you can also write scalar one, anything. Okay. So scalar is equal to min-max scalar and leave the parenthesis blank. So a scalar object is created, but it is just created. It has not yet been applied on my data frame. Now here, what is my problem? In previous case, here I had only one column, so scaling was easy. I could have done by the basic definition, that find difference of each observation from and minimum and put them in the another column and divide that column by difference of each observation, difference of maximum minus minimum, and whatever values you get, they are your scaled values. But here, and the answer here came out to be between 0 and 1. But here there are 3 columns. So I cannot afford to scale these separately, income, then age, and then education, these 3 columns. Okay. So I have to apply min-max scalar directly to the entire data frame. So that is done this way. First you create a scalar object, and then just use this much, scalar dot fit transform, fit underscore transform. Now fit transform is applied to what? df. You can also apply to df in square bracket under in quote income. Then it will be only applied to income column. Similarly, df in square bracket in quote age. Then it will be applied to only age column. Similarly, df in square bracket, you can write in quote education. Then it will be only applied to the education. But here I am applying scalar dot fit transform to entire df, and columns on which I am applying is df dot columns. What is df dot columns? If I write one more cell here, all columns. Okay. So df dot columns is equal to all columns. So that means this line is very important, because you are seeing this line for the first time. So there are only 2 steps, and this is min-max scalar for normalization, but for standardization also the steps are identical. The only thing is name changes. This is min-max scalar, where the name is standard scalar. So first you create a scalar object and then apply that scalar object to the entire data frame, or to all the columns of the data frame, by using this command, scalar dot fit underscore transform. Data frame is the argument, and columns which you should include is df dot columns. Okay. Let us print the scaled data frame. Now this was my original data frame. The values were between 45,000 and maybe 65,000 maximum and minimum. Here you can check the values are between 0 minimum and 1 maximum. Okay. Here the values were minimum 25 and maximum 45. Here you can check minimum 0 and maximum 1. So that means here also minimum 0 and 1. Here also minimum 0 and maximum 1. Education had minimum 12 and maximum 18. Here education had minimum 0 and maximum 1. So the row which was minimum still remains minimum. The row which was maximum still remains maximum. But here each and every column was over a different ranges, while here all the columns after applying min-max scaling are in the range 0 to 1 only. Now that is a big advantage, because earlier also we have seen that if you build a model directly using this data, then this income variable that will dominate the prediction unnecessarily, because the values are pretty high in that. It is in thousands. Okay. While age and education, they are only 2-digit variables. So you have to first ensure that no feature should dominate excessively to the model. So when you do this scaling, now you can see the range of income is also 0 to 1, range of age is also 0 to 1, and the range of education is also 0 to 1. So now every feature is equally dominant. So that is one thing. Now, when to use this min-max scalar? The min-max scalar is used when you need to bound values but assume nothing about distribution of data. Now, again, what is meaning of that? Understand. There are two types of algorithm or model building tools. Some require that the data which is fed into them is normal, while some do not require any such thing. Whether the data being fed to them is normally distributed or anyhow distributed, they don't care. They don't care means they give equally accurate result. And what is normally distributed? In the shape of that bell curve. We have already seen many times that you know that Gaussian or normal distribution is nothing but the bell curve. So if you are going to use an algorithm for which data distribution is normal is not a condition, then you can use min-max scaling, because min-max scaling does not guarantee that the data distribution is normal. So you will not get bell curve. Okay. Now let us plot this. Now this whole looks very complicated, and it is complicated. But what I did was I just give these two data. That this is my original data frame, this, and this is my min-max scaled data frame. Okay. So that is this. Now I just give these two to the coding tools, and I ask that give me Python code by which I can put I can plot data distribution of original data frame and scale the data frame also. So you should not be confused from where these values are coming. These values are coming because they were given to me. Okay. And from where these values are coming? These values are coming because when I scaled it by applying min-max scalar dot fit transform, okay, then that give me these values. So I'm just using those values, but I'm providing the values in the form of a Python list. So if I plot that, and you see an interesting thing once again, that this is the distribution of original income, this is the distribution of scaled income, this is the distribution of original age, scaled age, and original education and scaled education. So when you create a scalar object like min-max scalar, like this, and then when you apply that scalar object to entire data frame, all columns of entire data frame, how you will apply? Scalar dot fit underscore transform in parentheses the data frame, okay, and answer other argument will give how many columns to include. So I'm saying that include all columns. So columns is equal to df dot columns. So df dot columns is the list of all the columns of the data frame. So when I do that, I'm getting this answer. But the values may have completely changed, but the data distribution for the original and the new for each and every three columns, income column also, age column also, and education column also, that has remained the same. Now this is very important. That means you are making all of them to come between the same range, so that 0 to 1, this is 0 to 1, this is also 0 to 1, and this is also 0 to 1, so that none of them dominates the model or prediction process excessively and unduly. Otherwise, these are having large values. So it may be possible that the model which you are building or the equation which you are building takes excessive effects due to that income variable. But we have now converted and brought everybody on same scale. That is the meaning of word scaling. And what is that same scale? 0 to 1. Then that process is called min-max scaling. We can even plot another plot. You can see before and after, the values may be totally different, but data distribution is totally equal. And you can see here the values were 12 to 18, but now the values vary from 0 to 1. Here the values were 25 to 45. Now the values vary from 0 to 1. And even income was interesting, that values were very over a very big range, 45,000 to 65,000. But even it now varies from 0 to 1. So obviously, if you use this kind of data, now all the columns will have equal effect on the response variable, and all are equally responsive. This is data distribution, but I can also plot something called kernel density plot, like this. Again, don't bother from where this kernel density plot is shown by KDE, kernel density estimation. Okay, but it shows that original data was like this bell curve, the new data is also like this bell curve. The scale has completely changed, 30,000 to 80,000, that has changed from to minus 1 to plus 1, or actually speaking, majority of the values are between 0 to 1. Okay, then KDE of original age, that was not perfect Gaussian distribution like this, but it is still more or less Gaussian with a skew on one side. Okay, so then after scaling also, the scale on x-axis may have changed, but distribution is identical. And similarly, education again is perfect normal distribution, and after scaling also it is perfect normal distribution. So this is about that min-max scaling. So you don't have to do actually this kind of table making for every column, that take each observation and subtract the minimum value of observation and then divide by difference between maximum and minimum value of observation. No, then instead of that, what you will do, just import sklearn library, and from sklearn.preprocessing import that standard scalar, sorry, min-max scalar, and create a min-max scalar object. So scalar is equal to min-max scalar, and then apply that object. How to apply that object? Then it is scalar dot the object dot fit underscore transform, and to whom you will apply the fit underscore transform, then fit underscore transform will be applied to entire data frame. Okay, whole data frame, like this. So still you have to specify another argument. If you want to specify a subset, then here you can put a comma separated list, like maybe income comma age, in quotes, both. So then it will apply scaling only to income and age, and the education column will remain as it is. But if you want to apply scaling to all the columns, then you will write df dot columns, then it will be applied to all columns. That was about min-max scaling. Now next we want to talk about this standard scaling. So I thought I'd say that this is last lecture, but I think I will stop here and we will take last lecture next for standard scaling. Okay.